Our next speaker is Sebastian Melzer from New Mexico State University, and he's going to talk about point-free topology in some way.
Yes, thank you. Hello, everyone. I will be talking about point-free topology in some way, because this is quite a peculiar investigation that is going on with me and Guram initially, where we look at frames via their Priestley duals that is doing point-free topology by using points. So I guess it goes against the point of pointless topology. Well, today I'll be talking in particular about algebraic frames and their Priestley duals and various subcategories. So let me first tell you what algebraic frames or algebraic lattices are. Those are the complete lattices where every element is given by the join of complete elements below it. The name, as the name suggests, this is a very significant kind of object that occurs in universal algebra. For example, for every group, the lattice of subgroups will be algebraic. For every vector space, the lattice of subspaces will be algebraic, which is a specific occurrence of the fact that for every algebra, the lattice of subuniverses is algebraic. And similarly, the lattice of congruences of every algebra will be algebraic, and a particular instance of that is that the lattice of ideals of a ring is algebraic. And then I have one more example of these. Nachbin showed in 1949 that algebraic lattices are exactly the ideal lattices of joint semi-lattices. Now, because I want to talk about algebraic frames, they are exactly the algebraic lattices that are distributive. Now, when your lattice is distributive and algebraic, it will satisfy that frame law, the joint infinite distributive law that's on my slide. And just to remind you, frames, they are the point of study and they're the focus of study in point-free topology because they generalize the lattices of opens of a space. And some specific examples of algebraic frames are the following. We have arithmetic frames. They're also sometimes known as M-frames, but M-frames is also sometimes something else. So that's not terminology that I'm going to use. I'm going to stick with arithmetic frames. Another example is coherent frames and stone frames. And I want you to call your attention to something here, that how you could define them is by saying what the compact elements form as a substructure. So in an arithmetic frame, what happens is that the meet of two compacts will be compact. The way to say this is that the compact elements form a sublattice, because the join is always going to be compact of two compact elements. In coherent frames, you're just going to add the condition that the top element is compact, so then it will be a bounded sublattice. In the stone frame, you add the condition that compact elements are complemented, so they will be the Boolean subalgebra. And because I'm talking about point-free topology, I'm going to mention this adjunction briefly. We have topological space and continuous maps. We have frames and frame homomorphisms. Those are lattice homomorphisms that preserve arbitrary joins. And we have this adjunction restricts to a dual equivalence between sober spaces and spatial frames. Those are the frames that come from a space. They're isomorphic to the opens of some space. That's one way to characterize them. Now, because I want to restrict this to the algebraic case, or I want to talk about the algebraic case, I want to look at the topological space that correspond to those. Those are spaces that are called compactly based. That means they have a basis of compact sets. And I'm not going to look at frame homomorphisms in my category, because a more standard category for algebraic frames uses coherent morphisms. And topologically, they will correspond to continuous maps that pull back compact open sets to compact sets. And we will call those continuous maps coherent. And because I just gave the definition of frame homomorphisms that are coherent, I will just add it here. frame homomorphisms are coherent if they map compact elements to compact elements. And then we get this, I think, pretty well-known theorem, but it's also kind of a Folkler theorem. This is the first reference we could find. So there's this, we have, if you take compactly based Sober spaces and coherent maps and algebraic frames and coherent frame homomorphisms, those two categories are dual equivalent, which were shown by Hoffman and Keimel in their memoirs from 1972. And you can restrict this to the various subcategories of frames that I mentioned. And then you get different kinds of topological spaces that restrict from compactly based overspaces. For example, if you look at arithmetic frames, you're going to get stably compactly based spaces. That's just adding the condition that the intersection of two compact opens has to be compact. If you look at coherent frames, the dual category will be the spectral spaces, where we just add the condition that they have to be compact. So then the whole space, the top element will be compact, like we had in coherent frames. And this the category of stone spaces, which you could define in a similar way as I did with the stone frames, but the more standard definition is to say they're spectral, or that's one of the ways to define the spectral space, that is zero-dimensional. And so the usual morphisms in this category are continuous maps, but every continuous map between stone spaces is coherent, so that's why this is a full subcategory. And so this is what we've been doing. We've been applying Priestley duality to frames. So let me talk about Priestley duality. So what is a Priestley space? Let me start with that. It's a compact space with a partial order where you can separate elements with Klopen upsets. And the Priestley duality states that the category of bounded distributive lattices and their morphisms is dually equivalent to the category of Priestley spaces and order preserving continuous maps. Now, since frames are special bounded distributive lattices, you can apply Priestley duality to it. And what you get is, because frames are exactly complete Heiting algebras, what we get are Sakia spaces that are Priestley spaces where the downset of a Klopen set is also a Klopen. And since they're complete, they will be extremely order disconnected Sakia spaces. That means that the closure of every open upset is going to be a Klopen upset. So in Priestley space, they will always be closed upsets, so we add the condition that they're open. Now, what we call L space or localic space, that's an extremely order disconnected Sakia space. The localic morphisms, so the morphisms that correspond to frame homomorphisms between frames, they are the order preserving continuous map where closure and inverse image commutes for open upsets. And then if you say that L Pries is the category of L space and L morphisms, this was a result by Kurt and Sichert from 1988. The category of these spaces, localic Priestley spaces, is dually equivalent to the category of frames. So that gives you the non-point free approach to point free topology. So one of the first things I want to mention is how spatiality occurs in these Priestley spaces. If you look at the frame and let X be its dual, then we define the subset, the spatial part. I will denote it by Y. It's all the elements in the space whose downset is Klopen. If you come from a frame, this will be exactly your completely prime filters. If you see your Priestley dual as the prime filters of that space, of that frame. So we call an X space, we call an L space, an SL space, if this set is dense in X, and we let SL Priest be the full subcategory of spaces where Y is dense in X. And I already said this a little bit, but we can view Y as a topological space by restricting the Klopen upsets of X down to it, with it, and that will be exactly the standard way to view the spatial part of the space of points of that frame. And this, we get this theorem. The first part is more like a lemma, but L will be spatial exactly when Y stands in X. I already said this, I guess. But here it's written. And then we get from that this theorem that the category of spatial L spaces is equivalent to sober spaces by mapping X to Y. And it's dually equivalent to a class of spatial frames by restricting Pulse-Sichler duality. And now we can talk about algebraic frames. So what makes algebraic frames special? They have a lot of compact elements. And what are compact elements in my Priestley space? They are special Klopen upsets. We call these Klopen-Scott upsets. And what is a Scott upset? It's so I have this picture here, but the definition says we have a closed upset. If its minimum lies inside the spatial part, then it is a Scott upset. Right, so I have this closed upset. If its minimum lies inside my spatial part, then this is a compact. This corresponds to a compact element. So in an algebraic L space, we have a bunch of these Klopen-Scott upsets. So this is how we define it. If we have a Klopen upset U, we look at what we call the core. It's the union of all the Klopen-Scott upsets contained in that Klopen upset. And an L space will be algebraic if core U is dense in U for every Klopen upset U. That means we have enough Klopen-Scott upsets below that Klopen upset. And then you get the expected theorem. At least this is the theorem we would want to get. L is an algebraic frame if and only if X is an algebraic L space, if and only if the spatial part is a completely based sober space. So this describes the object level of this category, or the Priestley duals of algebraic frames. Let's look at the morphisms. So when are these L morphisms coherent? Again, we can define it in terms of this core. It's simply saying, if I take the inverse image of a core, it has to lie inside the core of the inverse image for every Klopen upset. The other inclusion is always true, so we could put an equality here, but this is the important part. And then we get the duality by restricting the previous theorem for spatial frames. We can now get this theorem that algebraic L spaces are equivalent to compactly based sober spaces and dually equivalent to algebraic frames. And for the rest of this talk, I will restrict this duality to the subcategories that I mentioned before. So we have to categorize those objects in terms of the Priestley space. So first I have arithmetic frames. What makes a frame arithmetic? Well, it's when the core of the Priestley dual becomes, in a way, a meet homomorphisms. It will commute with the intersection for all Klopen upsets. Now, if you were to translate arithmetic directly into the language of the Priestley space, you would say something like, the intersection of two Klopen-Scott upset has to be a Klopen-Scott upset, because you want to say the meet of two compact elements is compact. You know, that's not exactly the same. This is, in my feeling, a more natural condition, but it's equivalent to this one. This condition is equivalent to saying the intersection of two Klopen-Scott upsets is a Klopen-Scott upset. But we can define it just in terms of the core. And then I will say this category, arithmetic L spaces. We just take the full subcategory, same morphisms. We can restrict the theorem. We get that arithmetic L spaces are equivalent to stably compactly based spaces and dually equivalent to arithmetic frames. And to characterize coherent spaces, you have to add the condition that the frame is compact, saying the top element is compact. How does that how does that occur in the Priestley dual? Well, that just means if I take the core of the whole space, it stays the whole space. So it becomes a top homomorphism in an array because it maps top element to top. And we call the arithmetic if it is coherent and L compact. Again, if we restrict the theorem, now we get that coherent L spaces are equivalent to spectral spaces and dually equivalent to coherent frames. Finally, I want to talk about stone frames. But first, to talk about stone frames, I need to talk about zero-dimensional frames. So I will remind you what zero-dimensional means. It means every element of that frame is the join of complement elements below it. Complement elements correspond to Klopen upsets that are also downsets. We call such sets Klopen bisets. And similar to how I defined the core, we can define a center of a Klopen upset. We take the union of all the Klopen bisets below it. If this set is dense for every Klopen upset, then we call the space zero-dimensional. And the frame will be zero-dimensional if and only if its Priestley dual is zero-dimensional. Both of them will imply that the spatial part is zero-dimensional, but the converse of that is not necessarily true. If you don't have enough points, you will not get zero-dimensionality back. But if the spatial part is dense, so that's saying L is spatial, then you get zero-dimensional the other way. So then a stone L space is defined as an L compact zero-dimensional L space. And we define a category. Here we take L morphisms, so not coherent ones, but that's actually a lie. Every L morphism between stone and L space will be coherent, and hence it's still a full subcategory of the previous one. And we can restrict the previous theorem. You get that stone L spaces are equivalent to stone spaces and dually equivalent to stone frames. And to give a short summary of what just happened, we have these kind of folklore dualities going this way, and we gave a new proof of them by looking at their Priestley spaces and proving these dual equivalences and these equivalents directly. So this gives an alternative proof for these dualities, and it gives us a good, this gives us an idea of what these spaces of frames look like. It gives us a way to study frames with points, even pointless frames you could study with the Priestley space, which give you a space to study. Anyway, thank you. I also want to thank the organizers for the support and the Department of Mathematical Sciences at NMSU. Thank you.
Any questions? No questions. Let's thank Sebastian again. Next talk is going to be in 15 minutes.